But before we get started, we just are going to do a real quick recap of what we spoke about on Wednesday last week, because your ability to work with cubic functions and your ability to find cubic function equations is incredibly important. You'll see if you go through any past paper, about half of your calculus marks, so about half of those 35 just deals with cubic functions. So you need to be comfortable with your cubic functions. So on Wednesday last week, we spoke about two different ways or two different scenarios in which you can find yourself when determining the equation of a cubic function. We spoke about what happens when I give you the x-intercepts, and so you can use the x-intercept formula of your cubic function. Alternatively, when you're given the turning point, excuse me, as in this situation, and we have to remember that turning point implies first derivative equal to 0. So we did do an example like this on Wednesday, but I'd like to do another one just so we're all comfortable with this, because the x-intercept scenario is a lot easier to handle than the turning point, because of the fact that with turning point we have to work with the derivative. Okay, so we're going to have a look at this first example. Obviously, you're more than welcome to go ahead and give it a try by yourselves if you want to, but I'm going to do this first example and then we will get into our derivatives. Whoopsie, sorry, and we'll get into sort of more complex graph interpretation questions when it comes to cubics. So what we've been given here is p of x, which is defined by x cubed plus 5x squared plus 4x plus d. We've been asked to determine the values of a and d. So always just look very carefully at what those values represent. A would represent, or rather the sign of a would represent whether or not this cubic is positive or negative. We can see that because this cubic, sorry guys, we can see that because this cubic initially decreases, then increases, then decreases, it is going to be a negative cubic, which means that our value for a should be negative. And we can see that d, or we know that the d value, that constant, is going to be the y-intercept. Now, if we go and look at where our y-intercept is, it is a negative y-intercept. And so again, our d value should be negative. These are just things that you can sort of already start thinking about before you get into your question, so that when you get your answer, if you end up with a being positive, you know you've done something wrong. If you end up with d being positive, you know you've done something wrong and you can go and double check yourself. So it's always important to just take a second, analyze the information you've been given, and then you can start with all your working out. All right, so if we assess what information we have been given in this question, we have only been given a turning point. So we've only been given b. Now, because b is a turning point, we just need to be mindful that that means first derivative. So turning point is where our first derivative is equal to 0. Okay, so we're definitely going to have to use that, but what we also just need to remember is that any time we're solving for two unknowns, inevitably that means simultaneous equations. Inevitably what that means is that I'm going to have to come up with two equations in order to solve simultaneously. So let's think about those two equations. Well, we know we have to use the first derivatives. That's one equation. If you look at b, b is just a point on this graph. So we could substitute those x and y coordinates into p of x's equation and get an equation or an expression in terms of a and d. So just remember, yes, b is the turning point, but it's also just a point on the graph. And so it can fit into both, or can be substituted into both your original p of x equation as well as your turning point. Now, it doesn't matter which one you start with. It is completely up to you. I've already written down turning points, so I'm going to go with that. Right, what that does mean, however, is we need to find the first derivative. Now, grade 12s, remember, do not use first principles unless we ask you to. Use the little trick that we spoke about. So take the exponent, times it by the coefficient, and then subtract 1 from the exponent. Move on to the next term. Times the exponent by the coefficient, subtract 1 from your exponent, etc., etc. Remember, constant terms fall away. So that d is going to fall away. Now that is wonderful, because what that means is actually now I'm going to have an equation just with a that I need to solve. Lovely. This is turning point, so first derivative must be equal to 0, so we can replace, or we can make this equate to 0. And remember, we know the x coordinate of the turning point. We know it's at 2. So in place of x, we can substitute 2. Right, and then like I said, what's great is that because d is the constant and we found the derivative, it's fallen away. So now we can just go and solve it for a. So 0 is equal to 12a plus 24, which means that 12a is equal to negative 24, which means that a is equal to negative 2. Now remember we said right at the start, a should be negative. It is negative. It's a decreasing cubic function, so a should be negative. We've got an a value that matches up with what we expected. We now need to go ahead and find d. Now remember, d is in the original expression, but not in the derivative. So that means we're going to have to go back to our original. Now, we know that a is negative 2. I'm going to substitute in everything I know now. And we know our turning point b is at 2, 9. So I can substitute a, 2, and 9 into this equation. So 9 is equal to negative 2 cubed plus 5 times 2 squared plus 4 times 2. Oh, golly, who knows what happened there? Fix that. Plus d. So now we've got a whole equation in terms of d, and we can go and solve from there. Right, this is just a simple case of typing into your calculator and getting what d is equal to, but we end up with d equal to negative 3. Remember again, we said that d should be negative because our y-intercept is on the negative y-axis, excuse me, and so both of those values make sense for the graph I've been given. If you needed to, or if you were asked to give your functions equation, that's easy enough for us to do. Negative 2x cubed plus 5x squared plus 4x minus 3. And so now we know the equation of p of x. Right, so when it comes to turning points, just bear in mind that first derivative equal to 0 is very important because of the fact that you've been given a turning point. Excuse me. Alrighty. So let's take a screenshot of this and then we'll have a look at the next one. I'm going to ask you guys to do a few of the questions in the next one so you can get ready for that. All right. So example 2, once again, we've been given a cubic function. We've been told that f of x is equal to x cubed plus bx squared plus 24x minus 20. It's sketched alongside. Now, guys, just remember, I said not to scale here, but you should remember that your diagrams are never necessarily drawn to scale. So don't rely on guesstimating coordinates, if that's the appropriate way to say it. It's not necessarily to scale. We get it looking correct, so x-intercepts where they should be, y-intercepts where they should be, but it's not to scale, so you can't go and measure, essentially. Right, it then goes on to say that A at 2, 0 is the local maximum turning point, B is the y-intercept of f, and C is an x-intercept of f. D is the local minimum turning point, and E is the point of inflection of this graph. And then we've got 5 questions here. So the first question is asking us to determine the values of A and B, and let's just be clear about which those are. They are the lowercase letters. We're not asking for coordinates. So in this equation of f of x, I'm looking for A and B. Now, this is essentially what we've just done. We've just done a question that dealt with how, or looked at how you can deal with your turning point when you're given it to find the equation. So I want you guys to try question A by yourselves for me. I'll give you I'm going to give 3 minutes. You might need more than that. That's absolutely fine. I'll check in after 3 minutes, and then we will see where you're at. Obviously, if you've got questions as you go along, please ask. But let's give this one a try. And guys, just remember, look at your graph. This is an increasing cubic function, so A should be positive. So when you get your value of A, make sure it does actually align with your cubic function that you've been given. Okay, 3 minutes, I'll check in and then we'll see, but let's give this a try and obviously just ask questions as you go along, but it's pretty much what we just did just now with a new function. Right, in grade 12, obviously I've asked you just to do A, but if you want to just carry on and get to B, C, D, and E, that is more than okay. You're more than welcome to carry on. It has been 3 minutes. Can you just give me a thumbs up if you're done with the first one, or a thumbs down, just so I know you need more time? Thank you, Leila. Bulgile, have you got a question? Sorry.
Ma'am, I don't understand this one, man.
The question A.
Yes.
Okay, cool. Let's have a look. So let's go through it and let's have a look, and then let me know if it makes sense once I've gone through it. Okay.
Yes, ma'am.
Cool. Alrighty, guys. So if we look at this first one, what you have been given in this case is your turning point. The second you see a turning point, you need to be thinking first derivative. All right, because where your first derivative is equal to 0, you know you have a turning point. So for question A, that's the first thing I'm going to do. I'm going to work out the first derivative of f. So you're looking at my equation there that I've highlighted in yellow at the top. We use our trick. So 3a x to the power 2 plus 2bx plus 24. And we know that where that first derivative is equal to 0, I find my turning point. So 0 equals 3a. Now, at this turning point, the x coordinate is 2. So we can substitute that in. Remember, we are saying, or when we find the first derivative, we are looking for an expression that gives us the gradient at that point. And here, because it's our turning point, we make that gradient equal to 0 because the tangent line at your turning point is horizontal. So we can substitute in the x coordinate that we know. So this would be 2 squared plus 2b times 2 plus 24. Right, now we're going to have an equation in terms of a and b. So 2 squared is 4 times 3, so this is 12a plus 4b plus 24. We can simplify all of that by dividing everything by 4. So 0 is equal to 3a plus b plus 6. You don't have to simplify it if you don't want to. It's up to you. It will make your life easier a bit later on, but you don't have to immediately if you don't want to. Okay, so we've got an equation in terms of a and b, which is great because we've been asked to find the values of a and b. But the second we've got two variables we need to solve for, we need to have a second equation. Now remember, this point is on the graph, so we can substitute this into f of x. So the y is 0 and the x is 2. So 0 is equal to, into the original equation, a times x cubed, so 2 cubed, plus b times x squared. Obviously, we know x, so now I'm writing x. So b times 2 squared plus 24 times 2 minus 20. Right, so again, we've got an equation in terms of a and b, so we're going to be able to solve simultaneously. If you simplify all of this, 0 is equal to 8a plus 4b plus 28. Once again, we can simplify this. We can divide everything by 4. So 0 equals 2a plus b plus 7. So what we now have is a situation where we have got two equations, both in terms of a and b, and now we can solve simultaneously. Now, guys, how you choose to do this is up to you, and I've said this to you before. You pick the method that works for you. But because in both of these equations, because in both of these equations I have a positive 1b, I'm going to isolate b in both of them because then I can just equate them. So in this equation, b is equal to minus 3a minus 6. And in this equation, b is equal to negative 2a minus 7. Because the b's are the same value, b is equal to b, what we can now do is we can go and make these two equal. So minus 3a minus 6 is equal to negative 2a minus 7, and we solve for a. So this would be negative a is equal to negative 1, and so a is equal to 1. Now remember we said a should be positive because it's an increasing cubic function. A is now positive, so we've got that perfectly on the head. Right, we then need to go and find b, but just remember that you have got two equations that represent b. We've got off. It's a little aggressive. Right, we have the first equation that we worked out over here, as well as the second equation. It doesn't matter which one you substitute back into. Okay, it makes absolutely no difference. So let's just go here. B would be equal to minus 2 times 1 minus 7. So B is equal to negative 9. Sorry, I thought I heard something weird. We were asked to find the values of A and B. We've done that. Obviously, if we want to, we can just go and write our equation out. So f of x is equal to x cubed minus 9x squared plus 24x minus 20. But once again, great told, when you're given the turning point and you've been asked to find the formula of your cubic function, when you are given that turning point, you need to find the first derivative equal to 0 and substitute in the x value of your turning point. And then you need to find your second equation.
Ma'am,
Yep.
how did you find the value of A?
The value of a. Okay, so are you with me in terms of getting, so you're with me in terms of finding first derivative and getting this equation and substitute?
Yes.
Okay, cool. So once we've got those two, what I saw was that both of my equations had a b. Now you don't have to do it like this. You could just go isolate b from one equation and then substitute it into the other equation. That's absolutely fine. You're going to get the same answer. But what I saw was that because both of these equations had a b, if I isolated b in both of my equations, I could just make them equal to each other because b is the same thing as b. So I took the negative 3a minus 6 and made it equal to negative 2a minus 7 because they both represent b, and then I solved for a.
Okay.
Okay. So guys, like I said, there's lots of different like variations of substitution for simultaneous. As I said, you don't necessarily have to do it like this. You could isolate b in one of the equations and then substitute it into the other. I just chose to do it like this because I saw two b's. You really don't have to do it like this. You could also use elimination. I don't know how many of you remember elimination from grade 10, but that could work here as well. You decide which works best for you, but if you are more comfortable isolating the variable and then substituting it into the other equation, then that's what you do. All right, it's whatever you're comfortable with. All right, but now we've got our equation of our cubic, and so what that means is we can now hopefully go and get the rest of these answers. So question B asks for the coordinates of B. Who can tell me what is special about, oh, it's a bit aggressive, but anyways, what is special about point B? What is it to the function? If you're not too sure, read the information again. What does it say point B is?
It's the y-intercept, ma'am.
Nice. Okay, good. Well done, guys. All right, so exactly, it's our y-intercept. Now remember, your y-intercept is where x is equal to 0. But more importantly, in your equation, your y-intercept is this constant term. So we know that the y coordinate at b is at negative 20. So what that means is that for question B, our coordinates of B are at 0, negative 20, because that is where we will find our y-intercept. So always just look carefully at your graph, make sure you know what point is which, because that required absolutely no working out on our part. We had to do absolutely nothing. And we got our answer. Okay, if we now go to question C, it says the length of AC. Now again, just take a moment, assess what information you have. The length of AC is asking me essentially for the distance between your two x-intercepts. Now we know where one of our x-intercepts are, and more importantly, we know that because it's also a turning point, if we were to factorize, we must have two brackets of x minus 2. But unfortunately, we don't know where the second x-intercept is. And so what that's going to mean is that for question C, I am going to have to find my two x-intercepts, which takes this arrow off. All right, now we have got our equation. Okay, f of x is equal to x cubed, already forgotten, minus 9x squared, plus 24x, minus 20. I don't know. And we can now go find our turning points. Now, guys, remember our turning points, our x-intercepts. Remember, when we're finding our x-intercepts, we need to factorize this cubic expression. Now, we already know that one of our solutions is at a, so x minus 2. And now we have to find the corresponding quadratic. So this is going back to our factorization of cubics that we did last week, week before, I think, or week before. All right, so to get our quadratic, what we need to do is we essentially need to sort of work backwards. So we know that x times x squared will give me the x cubed that I want. I then move to my constant. Negative 2 times positive 10 will give me that negative 20 in my original cubic. So I've got the first and the last term. I now need to decide on my x term in the middle. Now, the way I do this is I say, okay, if I were to say negative 2 times x squared, that gives me negative 2x squared. And I need to get negative 9x squared. So I need another negative 7x squared so that when I add up all my x squared terms, I am going to get a negative 9x squared. So that means that when I multiply x with whatever this middle term is, I must get negative 7x squared, which means that this middle term must be negative 7x, because x times negative 7x gives me the negative 7x squared that I want in order to make the negative 9x squared. All right, so if you are not too sure how to factorize cubic, go back to our lessons from, I want to say 2 weeks ago. It's all there explained for you on how to factorize a cubic. Right, once you've got that quadratic, you factorize your quadratic expression. So this would be x minus 5, x minus 2, and so you get that x, and remember this is where it's equal to 0 because it's your x-intercepts, x is equal to 2, or x is equal to 5. Now we already know x is equal to 2. We know where A is, but now we know that C is at 5, 0. Sorry.
Ma'am,
yes.
if you do not want to factorize, can you use the synthetic method?
Yeah. So remember we spoke about the synthetic division. You're more than welcome to use that. I do find it gets quite tricky when you get to more complex cubics, but yes, you're more than welcome to use that method.
Okay.
Okay, so guys, yeah, there are other methods to factorize your cubics, the synthetic division being one of them, and we did do some examples using synthetic division. So again, if you want to have a look at that, you can go to those lessons. Honestly, as long as you get your x-intercepts, whatever method you use, I'm good. All right, so guys, now we know that that C is at 5, 0, which means that we can now say that the distance between AC, or A and C, is 3 units. Once we knew where our two x-intercepts were, it was then easy to count the distance. A is at 2, C is at 5. That is a distance between the two of them of 3 units. All right, so you need to have both, but once you've got that, it's counting. All right, question D asks for the coordinates of D. Now, remember they told us that D was our local minimum. So in the information of our question, in case we've forgotten, D is the local minimum turning point. Here it is. And we already know that to find a turning point, we need to take the first derivative and make it equal to 0. So that is exactly what we're going to do. I don't know why I'm panicking here, but I apparently am. Right, so question D. Anyone? No? Okay, it's quite an aggressive D, but it's fine. We want the first derivative. Now we've got the equation of our cubic, so we're just going to use that. That gives me 3x squared minus 18x plus 24. This is where, or the turning point is where your first derivative is equal to 0. And now we're going to go ahead and factorize this quadratic. Now, great tools, remember you do have the quadratic formula. If you don't want to sit and try and factorize this, don't. Just use the formula. For whatever reason, I choose to make my life difficult and I do factorize it, but you do whatever you're comfortable with. Everything can be divided by 3, so this would be x squared minus 6x plus 8. And so my factors would be x minus 4 and x minus 2. And so my x-intercepts are at positive 4 or at positive 2. Now we already have the positive 2 one. That's at A. So we don't need to go and deal with that. That's done. But I do need to deal with this 4. Now remember, what you're going to do is you're going to substitute this back into your original. Right? So what this means is that f of 4 is equal to 4 cubed minus 9 times 4 squared plus 24 times 4 minus 20. And you substitute it back into your original equation. Once you do that, you get negative 4. And so that means our turning point D is at 4, negative 4. I really have chosen to squish things here, but anyways, it's okay. So turning point, first derivative equal to 0, factorize, substitute that x value back into your original cubic function to get the corresponding y. And so we have the coordinate of D. Alrighty, we haven't practiced the next one a lot, but we have been asked for the coordinates of E. Now remember, again, if we go back to the information of the question, this is why it's so important to read this stuff. E is our point of inflection. Does anyone remember how to determine the point of inflection? How do we work out the point of inflection for a cubic function? Does anyone remember? If it helps, you would have done this with teacher Kirsty when you spoke about sketching cubic functions for the first time. Don't know if that gives you a hint.
I think the second derivative must be equals to 0.
Excellent. Exactly, guys. Point of inflection is where your second derivative is equal to 0. Amazing. Awesome. Okay. Now we already know what the first derivative is. We just found it in question D. So here's our first derivative. Hello? No? Cool, cool, cool. Okay, that thing that's now highlighted. That's our first derivative. All you do to find your second derivative is literally find the derivative of the derivative. So we're going to use our trick. 2 times 3 is 6. X to the power of 1 minus 18. Now, guys, we've spoken about this before. If your original is cubic, your first derivative is quadratic. So remember, the powers decrease. It started with a power of 3. It's now got a highest power of 2, which means the second derivative will be linear, just an x. So I know I've done this correctly because it's linear. And exactly, we now need to make this equal to 0. We can then solve for x. So 6x is equal to 18, which means x is equal to 3. And then once again, to get the corresponding y coordinate, we substitute this back into our original equation. Okay, it's always back into the original because it's the corresponding y on the graph. So this will be f of 3. So this would be 3 cubed minus 9 times 3 squared plus 24 times 3 minus 20. And we get a corresponding y value of negative 2, which means that E, our point of inflection, is a 3, negative 2. All right, so this question that we've just had a look at is very, very much the type of question that you can expect in an assessment. It deals with all of those important little tidbits that we've had a look at before. X-intercepts, first derivative, second derivative. It even threw in a nice little distance question. But this is very much the type of question you can expect in an assessment when it comes to cubic functions. Oh gosh, sorry. All right, so fully aware that there's a lot going on here. I have numbered everything. But hopefully we've been following. So let's take a screenshot of this. If anyone has any questions, obviously just ask. But we're going to get into now these graphs of the derivative function. These don't come up a lot, but they can be asked. They're very interesting as well. And it is important for us to be able to work with them. Okay. Right, I hope we have that. So let's get into this. Right, so when we talk about the graph of the derivative, let me make this a touch smaller so that we've got all three of them on the screen. So when we talk about the graph of the derivative, what we need to remember is actually what I've just said now, but I will write it all down for us again, is the fact that if our original graph is cubic, our first derivative graph will be quadratic, and our second derivative graph will be linear. And we have these three functions shown on the screen here. All right, now the next thing that you need to remember is that when we find the first derivative, what we are actually finding there is an expression for our gradient. So remember, first derivative gives an expression for your gradient. Your second derivative talks about concavity. Okay, concavity is basically where the curve of your graph changes from concave up to concave down. I will speak about these two things now. So this refers to concavity. We did speak about these on Wednesday, but just in case, if you have a cubic function, it's not the best cubic function I've ever drawn in my life. There's two parts to it. There's a part of this function that will be concave down. So where you see sort of a sad looking parabola, this will be concave. Oh, I do this to myself, down. And this is where your second derivative is less than 0. But we also have a part to this function that looks almost like a happy parabola. And this is now where we are concave up. This is where your second derivative is greater than 0. And as we've just done in this previous question, this exact point here, where that concavity changes, is your point of inflection. Right, so these things are very important to take note of, because we can now go and draw graphs to express these characteristics of our cubic function. Let's just do that. Alrighty. So if we go back to what we have here, this is basically everything I've just said. Because our first derivative is...
So, ma'am,
yes, sorry.
if there is a change in the concavity, it means it is the point of inflection.
Yes, exactly.
Okay.
Amazing. All right, so guys, as I said, your first derivative represents your gradient. So if we go to our graphs here, we haven't got an equation for them, but that doesn't matter. We don't need one. We can see that for this first portion of the cubic graph, I don't like what I'm doing. This first little portion of our cubic graph or cubic function, that is a positive gradient, right? That's why we've got a positive here. The graph is increasing. We then see we hit our turning point. Our graph now starts to decrease, hence negative gradient. And once we hit the next turning point, our graph once again starts increasing, hence positive. Because the first derivative represents the gradient, What that means is that the y values that we plot represent the gradient of our function. So all of these y values here are positive, representing the positive portions of my cubic function. And all of the y values below my x-axis are negative, representing the negative portion of my cubic function. Those turning points we know are very important. Those turning points we know is when our first derivative is equal to 0. And if you think about this, your first derivative is the quadratic. If you were to make that equal to 0, that would be your x-intercepts. So these x-intercepts represent your turning points of your original function. I'm just going to write that down. Oops. Turning point of original. So if I give you a parabola and say this is the first derivative graph of a cubic function, where you see the x-intercept, you automatically know the x-coordinates of your turning points. All right. So most of the time we work with these first two, the cubic and the quadratic. We don't often work with the straight line, but I put the straight line here just so we can be aware of it. But essentially, when you've got an increasing cubic function, it will increase, decrease, increase. Your parabola will have positive arm, negative, positive. If it was a negative cubic, okay, your parabola would then just be the other way around. I'll attempt to show you this now. Right, so if we had, just draw whatever the hell that is, okay. If we had a negative cubic, so decrease, increase, because, you know, that's exactly what I was trying to draw. Okay, I will make another attempt. Decrease, increase, decrease. There we go. Right, so this is where A is negative. Firstly, our graph decreases, so negative gradient. Then our graph increases, positive gradient. Then it decreases again, negative gradient. Which means our derivative graph would have to have, just draw an x-axis, would have to have a negative y value, then positive y values, then negative y values. Negative, positive, negative, to represent those gradients. So positive cubic, happy parabola, negative cubic, sad parabola. The parabola represents the gradient of our original cubic. The turning points on your derivative graph are represented by the x-intercepts. And the other little tidbit of information that is always quite useful to have is the fact that your turning point of your quadratic is the point of inflection of your cubic. Okay, so what I mean by that is wherever this x value is, that will be the same x value for your point of inflection on your cubic graph. Right, so like I say, these are the two that we work with most. We can deal with our linear function as well. If we go have a quick look, so original graph, just do this. This is a sad parabola portion. This is concave down. This is represented by a negative portion of your graph. If we then move after our point of inflection, we then have the happy parabola portion of my function. So that's concave up. That's where my straight line is, positive. Because remember, concave up, your first derivative is positive. Concave down, your second derivative is negative. All right, so that is what this translates to directly. So this is the negative portion, so where it's less than 0, and this over here is where it's positive, so where it's concave up. Once again, this point in the middle is your point of inflection. So point of inflection on your straight line, because point of inflection is where concavity changes. Your straight line represents concavity. Again, we don't work with the straight line a lot, but we can ask you about the straight line, so it obviously is important that we can work with it. All right, so let's take a screenshot of all of this, because as much as it looks a bit chaotic, it is very useful for us. And then let's look at an example of how this actually will be asked. How can we use these derivative functions in answering some questions? Obviously, if you have questions, please just ask. So we're going to have a look at an example now. Sorry, guys, I will make it bigger again. Okay. All right, so let's see this first example. It needs to be so much bigger if we're going to deal with this. Right, so we've been told that the graph of y, which equals f dash x or f prime x, where f is a cubic function, is sketched below. So firstly, I'm telling you that I have given you the derivative function. I know it's a derivative function because of the notation. I'm also telling you that the original function is cubic. That makes sense. If my derivative function is a parabola, so quadratic, it means that the original must have been cubic. This first question is asking us, this first question is asking us for which values of x is the graph of my derivative, so the parabola, decreasing. Right, so let's go have a look. My parabola is decreasing from the turning point all the way essentially to positive infinity. That is where the graph is decreasing, goes down. What that means is I need to figure out the x coordinate of my turning point. Now we're sitting there thinking, well, I don't have the equation. How must I do that? Remember, your turning point is the line of symmetry of your parabola. So if you were to fold your parabola in half on its turning point, you create a mirror image. What that means is that the distance that each of your x-intercepts are away from your line of symmetry is identical. So whatever this distance is to this distance, so from x-intercept to line of symmetry to x-intercept, is exactly the same. So we can go and work this out. We know that the whole distance from -4 to 1 is 5 units. Cool. 5 units. Which means that each half on either side of my turning point must be 2.5 units. And guys, symmetry and parabolas is so important to remember because it is so useful. Right, what that means is my turning point is 2.5 units away from each x-intercept on either side. So you can go either way, it really doesn't matter. I'm going to go from 1. 1 to the y-axis is 1 unit, so I need to go another 1.5 units on the other side, which means that this x-intercept here is at -1.5, which means that my x-coordinate of my turning point is at -1.5. And so now I can say, well, this is decreasing for everywhere where x is greater than -1.5. So again, the ability to use symmetry with your parabolas, so useful, so important, and this is shown here. I didn't actually need any information about my graphs equation in order to figure out what the x value of my turning point is. It also means that I do know the x value of my point of inflection now, because remember, turning point of parabola is the point of inflection on your cubic function. All right, question B asks, at which value Kilobogile, sorry.
I cannot understand, Sham.
Which part don't you understand?
A. Number A.
Let's do it again. Do you understand where the graph is decreasing?
No, ma'am.
Okay, so let's have a see. So guys, remember graph decreases. You always read a graph left to right. So if we go to our parabola, this is going up. So this is where our graph is increasing, where the gradient is positive. We then hit the turning point, so that would be where the gradient is negative. And after the turning point, we now go down. So this is where the graph is decreasing. So what that essentially means is that for all of these x values, from the turning point all the way down, and this arm, remember, just keeps going, keeps going. All of that I've highlighted in yellow is where our graph is decreasing. Does that make sense? Does that make sense?
Yes, ma'am.
Okay, cool. So what we now need to go and figure out is what the x coordinate of my turning point is. Oh gosh, that's not even a straight line. The reason we want to go and work out what the x coordinate of my turning point is because that is a line of symmetry. So basically, if you fold your parabola on its turning point, it creates a mirror image. We can use this fact to go and work out where this x value is. All right, so if we have a look, from this x-intercept at 1 to this x-intercept at -4, that is a total of 5 units, right? Because -4 to my y-axis is 4 units. From my y-axis to 1, that's another unit. So that means that's a total of 5 units from x-intercept to x-intercept. Now, because of my line of symmetry, I know that on either side, these two lengths are equal to each other. And because I know the whole length is 5, I know that this is 2.5, and this is 2.5. And so what that means is I can count 2.5 units from 1 to my line of symmetry, or from my line of symmetry 2.5 units to 4, and I can get what that line of symmetry's x value is. All right, so if we go and do exactly that, and we count our 2.5 units, 1 to your y-axis is 1 unit, but then I still need another 1.5 units after my y-axis. And so that means that this takes me to -1.5 on my x-axis. 1.5 plus 1 gives me the 2.5 units away from your line of symmetry. And so we're able to get where our x value for our line of symmetry is. Now, because we have that, we know the x coordinate of our turning point, and because it's all of these x values greater than your turning point, we know that it must be x greater than -1.5. So where it asks where is it decreasing, x greater than -1.5. Does that make a bit more sense?
Ma'am.
Yes?
Yes, ma'am.
Okay, cool. So guys, again, this the characteristic of symmetry and parabolas, so important and so useful. All right. The next question says, at which value of x does the graph of f have a local minimum? Give a reason for your answer. So let's go back to what we have. We've got a sad parabola here. Because my parabola is a sad parabola, so this is, remember, the derivative graph, what that means is that my original graph must be a negative cubic. So decrease, increase, decrease. What that means is that it first has a local minimum and then it has a local maximum. And remember, those x values correspond to your x-intercepts on your parabola. So this local minimum corresponds to our first x-intercept, and the local maxima corresponds to our second x-intercept. So at 1. So we actually know these two values. This is at -4 on the x-axis, and this is at +1 on the x-axis. And so it asks, at which value does it have a local minimum? Well, at x equals -4. And my reason for that is because f dash x is a negative cubic or negative quadratic, whatever you want to say. Don't know why I said negative cubic, negative parabola. Hence, our original graph f is a negative cubic. And because it's a negative cubic, it first has a local minimum and then it has a local maximum. All right, the last question, again, this is what we can sort of expect when it comes to derivative functions, is to sketch the graph of f. So it's asking you, take everything that you can see in your derivative function and now sketch our graph of f. Now, we already know that this is kind of more or less what it should look like. It's a negative cubic function. I know where the turning points are. And technically, because I've gone and worked out the x coordinate of my turning point, I know where the point of inflection is. Now, guys, it's a sketch. It's not going to be perfectly accurate. Reason being is because you've got all of these x values, but you don't have the corresponding y. That is not the end of the world. You plot what you have, and it's a sketch. It's not going to be perfect. So we know we've got a local maximum at 1, and we know that we have a local minima at -4. We know that our graph must decrease, then increase, then decrease. And we know that our point of inflection is at -1.5. Okay, so we have all of this information. We can now go plot it. This was not very well positioned. Let's fix that. Move it over. Right, so decrease, then increase, then decrease. Decrease, increase to point of inflection. Increase turning point is not the beautiful graph that we would like it to be, but it doesn't matter. And we have a sketch of our cubic function. Here's our turning point at -4. Here's our turning point at 1. And there's our point of inflection. Again, it's not going to be perfect because you don't have all of the y coordinates, but you can give a rough sketch, a rough idea of what it is your original function would look like. If I then gave you the equation, or we were able to work out the equation, we could then sketch it way more sketch it way more accurately, but we can't. So we just do the best we can in terms of the x coordinates we've been given. All right, guys.